A system of linear equations is when you take two or more linear equations and you consider them together on the same coordinate plane. So we're going to be working with linear systems of equations in this lesson. So it'll be important for us to jot that definition down. It's two or more linear equations considered together. Two or more linear equations, and I'm going to probably shortcut equation with EQN. Considered together. Considered together. There we go. Considered together. The solution to a system is the ordered pair that will make both equations true. It's the ordered pair. There's going to be one of them. The ordered pair in most cases. There are extraordinary cases that we'll talk about, but for the most part, the solution to a system is the ordered pair, the one ordered pair that will make both equations true. And that's the intersection point. So it's the point of intersection. So now that I say the point of intersection, you might say, well, what happens if there is no point of intersection? Well, then there's no ordered pair. Well, what happens if the two lines are right on top of each other? Well, then you'd have infinitely many solutions. So in most cases, lines are going to intersect in one point, and that point of intersection will be our solution. Here's our first example. So our first example has y equals 2x minus 3 and y equals x minus 1. We want to solve this by graphing, and that's why we have a graph to our right. There's different ways that we can solve systems of equations, but by graphing is what we're going to be doing in this video. So I'm going to graph this first equation, y equals 2x minus 3. I might even change the color. Not copy it. I want to change the color. Let's make it blue. And then let's get rid of the highlight. Okay, so our blue line, y equals 2x minus 3, we're going to go down to the y-intercept of negative 3. And then we're going to use our slope. So our slope is equal to 2, and we're going to put that over 1. So from that y-intercept up to right 1, up to right 1, up to right 1, and I continue to do this throughout the entire grid. So I'm not just doing this for a couple of points, I'm doing this through the entire grid. And then I take my straight edge, always use a straight edge. Always use a straight edge to draw that straight line. Okay, so always use a straight edge. Let's put that right here. Use a straight edge to draw a straight line. It makes sense, right? Oh, the line has to be straight. Yep, so we need to use a straight edge. And that could be the side of a gift card, it could be your driver's license, it could be an index card, it could be a ruler. But we definitely want to use a straight edge, most especially when you're needing the accuracy, which in this case you would need the accuracy. The next equation, y equals x minus 1, and change that to red, that has a slope of 1. So I put that over 1. My y-intercept is negative 1, so the y-intercept is negative 1. From that y-intercept, we're going to go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, and I'm going to continue that all the way through the grid, down 1, left 1. So I'm going to try and get as many lattice points shown as possible. Going to use my straight edge to draw the straight line. And the point that they share, I'm going to do this in purple, the point that they share, you might have noticed when you were making your points and that red point went right over the blue point, that's the solution. So the shared point is the solution. So our solution to this problem is 2, 1. 2, 1 is the ordered pair that both lines share. Both lines share. These lines are called intersecting. So we might refer to these lines as just intersecting. There's nothing special about them. We are going to come across some cases where it is interesting. This isn't too interesting, just two lines that intersect, and the point where they intersect is the solution. Okay, here's another example. We've got y equals x plus 5, and we have y equals negative 4x. So we're going to consider these two together on the same grid. Y equals x plus 5. We're going to go up to our y-intercept of 5, and then down 1, left 1, down 1, left 1, a double negative because the slope is positive 1. Or up 1, right 1, up 1, right 1, up 1, right 1, still positive. There's our straight line using our straight edge. And y equals negative 4x, well, that's the same thing as y equals negative 4x plus 0, so our y-intercept is 0, and then we're going to go up 4, left 4, up 4, left 4, I'm sorry, up 4, left 1, up 4, left 1. So up 4, left 1, our slope is negative 4 over 1. So I can either go up 4, left 1, or down 4, right 1. Down 4, right 1. Up 4, left 1. And we were able to see where these lines share a point, and that happened to be right here at negative 1, 4. So that's our solution. The solution, x equals negative 1 and y equals 4. These lines as well are just intersecting. So these lines are just intersecting. Nothing interesting about them other than the fact that they do give us a nice lattice point for an answer. Okay, here's one for you to try. Y equals negative 1/2 x plus 2, and y equals negative 3x minus 3. So you go ahead and try, and when you're ready to reveal the answer and see the work, go ahead and press play. Okay, if I graph this first equation, it should look something like this. So you should have something like this on your paper. Straight line, using a straight edge, very nice. Make sure you put arrows on the end. And then we have the second line. And it should look something like this. And I saw where they share a point. It's this one right here, and you should have gotten negative 2, 3. And these lines are also just intersecting. Nothing special, just intersecting at one point. Okay, here's an example. Y equals negative 2x plus 1. And y equals negative 2x minus 5. Let's solve this one. y equals negative 2x plus 1. We're going to go with the y-intercept of 1, and then down 2, right 1, down 2, right 1, down 2, right 1. I'm going to continue that pattern all the way down to the bottom of the grid, and then up 1, left 1, up 1, left 1. I'm going to go to the top portion of the grid, draw a line using a straight edge, and that's one of our lines. The second one is y equals negative 2x minus 5. So our y-intercept is negative 5. We can go up 2, left 1, up 2, left 1, and continue that pattern. But it seems just when I'm getting close, I stay in equal distance apart from that other line. So when I draw this, not because I can't see the intersection point, but because their slopes are the same, I'm going to get close as I go up 2, but then I'm going to go to the left 1, and I'm going to have the same slope. So these two lines will never intersect. These lines are parallel. And what makes them parallel is they have the same slope. Therefore, they never intersect. And if they never intersect, that means I'm not going to have a point that they share. Therefore, there's no solution. Now, no solution happens. It occurs when you have the same slopes, but different y-intercepts. Different y-intercepts. So our slope here is negative 2. Our slope for the second one is negative 2. But the y-intercept is 1. The y-intercept is negative 5. Those are different. So different y-intercepts, yet the same slope. Same slope. Okay, here's another special situation. We've got y, let's do 2x plus 4y equals 8. And then y equals negative 1/2 x plus 2. Okay, I can graph the red one pretty quickly. It's going to look something just like that. And then the blue one, I'm going to have to take this 2x plus 4y equals 8, and I'm going to have to put it into slope-intercept form. So we'll subtract 2x from both sides. That's 4y equals negative 2x plus 8. And then we're going to just divide each term by 4. So y equals negative 2 over 4 is negative 1/2. 8 divided by 4 is 2. So, oh, okay, same y-intercept. Maybe that's the answer. But down 1, right 2, down 1, right 2. Wait a second. They share all of these lattice points. Are those the only points they share? Well, no. When I draw my straight line, they share every point. These lines are called coinciding. These lines are coinciding. They share all points. Therefore, what we say here is that it has infinitely many solutions. Infinitely many solutions. Infinitely many solutions happens when you have the same slopes, not splotes, the same slopes, and the same y-intercepts. So when your y-intercepts are the same, then you have infinitely many solutions. When your slope and your y-intercept are the same, you have infinitely many solutions. Okay, so here's one for you to try. Y equals 1/5 x plus 9 and 5y equals x plus 45. Go ahead and try that and then come on back. The first graph, we're going to have to do some negatives here. If I do up 1, right 5, that's great because I get 1 point, but then I'm going to have to go down 1, left 5, down 1, left 5. So there's our blue line. Now we need our red line. So I'm going to take 5y equals x plus 45, and I'm going to divide each term by 5. That's going to give us y equals 1/5 x plus 9. Wait a second. That's the same equation. Here's our blue line, and here's our red line. That's the same exact equation. So that's going to be the same exact line. So the answer here is infinitely many solutions. Now in the next video we're going to talk about how we can write our answers for infinitely many solutions. How we can write our answers for infinitely many solutions. Let's make sure that I've got an example for you. I'm pretty sure I do. Let's see. Maybe not. Maybe I need to show you right here. So when we have infinitely many solutions, I'm going to take this and I'm going to copy these two to another page so that I can show you. It's not too terribly difficult, but when you have infinitely many solutions, here's our original problem. We've determined we have infinitely many solutions. How do we write that? As an ordered pair. Infinitely many solutions. So you might box that, but then there's going to be this ordered pair that has an answer in it. So we can write our ordered pair in terms of x, or we can write our ordered pair in terms of y. So we have an x-coordinate and a y-coordinate, an x-coordinate and a y-coordinate. We can write both coordinates in terms of x by solving for y. So if I say I want this in terms of x, then I'm going to have x comma some value for the y-coordinate. If I want it in terms of y, I'm going to have some expression comma y. This expression needs to be in terms of x. Well, what is y equal to? Y is equal to 1/5 x plus 9. So one of my answers could be x comma 1/5 x plus 9. So infinitely many solutions. I could write the answer as an ordered pair in terms of x. I could also write the answer in terms of y. So if I write it in terms of y, I need to solve for x. So what I'm going to do here is I'm going to say, okay, well, let's solve that for x. 5y equals x plus 45. Now, it doesn't matter which equation you take and solve for x, because remember, they're the same equation. Let me go back here. They're the same equation. So it doesn't matter which one you decide to work with when you have infinitely many solutions. I'm going to subtract 45 from both sides, and that will give me 5y minus 45. So this is what I can now put in to the x-coordinate, because the x-coordinate, x, is the same thing as 5y minus 45. So 5y minus 45, comma, y. And that sums up solving by graphing.